Let's have a look at some of the homework here. First one is one of the problems that already done here. It was this one, I think, anyway. Let's have a look. Yeah. So 221. All right, on 221, you've got biaxial stress given. You've got some material properties given. So you go from biaxial stress to biaxial strain. So that'll tell you the strain. Then using the strain, you can calculate the lengths of the sides or angles. Okay. So we went through this. You know, we had sigma x, sigma y, E, and nu. Plug all that in and get epsilon x is 0.0531. That means that the x edge there will get 5.31% longer. Originally, it's 15 centimeters, so it becomes now 15.8. 15.8 is 5.31% longer than 15. So what I'm doing there, I'm taking 1 plus the strain times the original length. Similarly, we can plug in the values here and find epsilon y. It's 0.0219. So that means the y direction gets 2.19% longer. And there I go, find the final length. 12 times 1 plus 0.0219 is 12.26 centimeters. Now in the z, you've got this formula here to find the strain in the z direction. Plug in the values, you get a negative 0.025. So that means in the z, it's getting about 2.5% thinner. So if I take the original 2 centimeters times 1 minus 0.025, I get 1.95 centimeters. The last one there is to find the shear strain. Take tau over g, I get negative 0.0625. So that means the original 90-degree angle in the lower left-hand corner has a strain of negative 0.0625 radians on it. That's the change in the angle. Now, a negative shear strain actually causes the lower left-hand angle to get bigger. So that's pi over 2 plus 0.0625 radians. So I've got a 90-degree angle there in radians, pi over 2, and another 0.0625 radians. So that's 1.6333 radians, which converts to 93.6 degrees. All right, now let's have a look at the sketch, which is what I was kind of interested in doing here. So we start off with a plate there that's 15 centimeters long, 12 centimeters high. But then as we calculate it, it's going to change length. The 15 centimeters will become 15.8, and the 12 centimeters will become 12.26. And then the gamma xy is negative 0.0625. Now, what gamma is the change in this angle B here. And I'm going to have a hard time with my pen drawing that properly. But what's going to happen to that is it's going to turn from a 90-degree angle into a 93.6 degree angle. And that's going to involve the rotation of two lines, BA and BC. The combined rotation of both of them will be that 0.0625 radians. So what I'm going to assume here is half the rotation occurs on each side of the angle. So BA rotates 0.03125 radians, as does BC. So if I take the rotation in radians times the original length, I'll get the delta, how much the point actually moves. Okay. So for this line, I got the 0.03125 times the original 15 centimeters. So that line moves 0.469 centimeters. It moves in such a way that this angle ABC gets bigger. So that means C rotates down. A will be 0.03125 times 12 centimeters, 0.375 centimeters to the right. That's what makes the angle get bigger if A, excuse me, to the left, if A moves to the left. Okay. So let's look at how we would draw this up. All right, now the first thing we're going to do here is decide on our reference point. It's going to be B. That's the point that I assume does not move. So what's going to happen then from B is this 15 centimeter line will become 15.8 centimeters. So C will move out. Now, each centimeter I'm representing with two small boxes. So 0.8 centimeters is one full box, which would be 0.5, that's half of a centimeter, plus 0.6 of the next one. So I'm placing that dot about 1.6 boxes, which if each box is half a centimeter is 0.8 centimeters out from the original position of C. Similarly, I'm moving D up a little bit to signify the 0.26 elongation there of A. So I'm moving A up and C out, and I'm moving them proportionally in amount to signify these deltas. 0.8 for C, 0.26 for A. But then I also need to represent this shearing strain on both lines. So I'm going to take C and I'll move it down by 0.469, which would be almost a full box, because a full box is half a centimeter. A will move over 0.375, with a full box being 0.5. That's going to put it right about there. So what I've done now with B being constant is I've shown the final positions of A and C. So to draw the final shape of that box there, what I'll do is I'll take B and connect it to A and C. Okay. And then once I've got those two lines drawn in, right there and right there, I'll draw in the other two parallel. So this line will be parallel to BC, and this line will be drawn parallel to BA, and that'll be the final shape of that object. Okay. So that's how that box was drawn up. All right. Now let's have a look at some of these other problems here. 281, which is due Monday. There is a solution available in Moodle. We're actually looking at it there. So let's get this a run and see how we would figure this one out. We've got this solid shaft, 6 centimeter diameter. It's got a strain of 80 Newton meters applied there. Okay, like so. And we want to find the maximum shear and the normal stresses, and also the stresses on that line AB. So when I'm doing this, whenever I'm doing these torsion problems, I want to get the moment of inertia, which is pi over 2 R4. So pi over 2, R would be 0.03, that's half of 6 centimeters, is 3 centimeters, which is 0.03 meters. Take 0.03 to the 4 and multiply it by pi over 2, I get I, 1.27 times 10 to the minus 6 meters to the 4. So now I've got I. Now I can find tau max, and I can also find sigma max because they're equal. Tau max and sigma max are equal, and they're equal to the basic formula for shear, TR over I. And this formula is on the back of your formula sheet on the left-hand side in the torsion category. You can have a look at it there. So I just plug in T, the torsion, 80 Newton meters, the radius, which is the radius to the outside of the shaft, like so, and then divide that by I. and I'll come up with 1.89 times 10 to the 6th, which is 1.89 megapascals. Now that's actually a positive value is what that is. Or excuse me, that's a positive or negative. That's a plus or minus. Both the shears and the normal stresses are plus or minus. Okay, now I can also find the stresses on that plane, AB, both shear and normal. Now to do that, I need to get the angle that I use to calculate stress, and that's from the vertical plane, measured positive counterclockwise. So that would be 28 and 90 makes 118. So that's the angle that you'd use in the formulas. Now there's formulas for shear and normal stress, again on the back of your formula sheet under the torsion category there. And they're actually the biaxial equations, but given the fact that sigma x and sigma y are 0, a lot of the biaxial equation cancels out. So these are kind of like special shortened equations that are used just for torsion because sigma x and y are 0. So there's the normal stress formula. And then here is the shear stress formula. So tau xy cosine 2 theta for shear, tau xy sine 2 theta for normal. All right, now what we got to do here is figure out what tau xy is. Now we know its magnitude, it's 1.89 megapascals. We want to figure out its sine. Okay, and here's how you can do that. Now, the first thing that's going on here is I have an applied torsion that comes over and down the front of the face of the shaft. The reactive torsion will be over here at the support, and that will go the other direction. It'll go up across the face. Well, what you do is you take the down on this side and turn it right into a shear that goes down on that face. And the upward torsion on that side, that'll become, excuse me, an upward shear on this face, okay? So that's where you start. You just take the directions of the torsions, both the applied and reactive torsions, acting on the face of the shaft, look at their directions, up or down, and just move those over as shears, up or down. That's what you do. And then realize that the other shears meet in the corners. Okay, so there you go. There's a shear element. Remember, there's no normal stress in the x and y directions. So that's the shear element that you'd get. Now, you'll notice from that shear element that the shear on this standard reference plane, the vertical x plane, is down. That'll rotate that element clockwise. So that's actually a negative shear. So we know that tau xy is negative, and we also know its magnitude is 1.89 megapascals. So that's what we plug in for tau xy on these formulas. The angle's 118, you double that and get 236. So you just run those numbers, and you get the two stresses, shear and normal, on the 128 degree plane there. All right. Now we'd also like to draw a normal stress sketch. Now the maximum, and that would be for the maximum normal stress. Just to illustrate this, I just like to draw that out. Now, to do that, what I'm going to do is start looking at these shears. Now there's actually two ways to do this, and we'll look at both ways. Why don't we just start with the visual way? Okay. So here's the shear element, the element with the maximum shear on it. It's in the 0 and 90 degree planes, like that. And then we've got shears acting on all four sides, like that. Okay. That one's down, up, and then meeting in the corners. This one's left and right. Now, to visualize the maximum normal stress planes, we know what the magnitude is going to be on those planes. It's 1.89. We know that the normal stress planes make a 45-degree angle, okay? Like so. So what I'm going to do, I'm going to draw a diamond inside of the box, like so. And then I'm going to look at those shears as though they're vectors. Now, they're not really, but this is just a way for me to visualize this. And I'm going to look at two adjacent shears and add them up like vectors and see what the normal stresses would be on the plane there. So, for instance, I'll take this shear and that shear. I'll mark them in black. If I add those up as a vector, I'll go to the left and down. So on this plane, the normal stress goes to the left and down. Okay. I'll come over here and I'll look at these two shears up to the right. So on that adjacent plane right there, the normal stress goes up and to the right. So on that 45-degree plane, I've got compressive normal stresses. Okay. Now if I look at this one, up, and that adjacent one here to the left, that acts up and to the left on this plane right here, so that's tension. And then the last one, down. And I'm running out of room here. I'll sneak it in up here on top there, to the right. So on this plane, down and to the right, tension. So I end up with this element here, and the magnitudes are 1.89 times 10 to the 6, shown right there. And I don't have my pen with me, actually. I'm writing with the mouse, so I'm not even going to try and write this number. But that number would go here, 1.89 times 10 to the 6, and there, okay? So that's visually how you can write up, how you can draw up the maximum shear element right up there, and the maximum normal stress element right there, okay? I'm going to give that a try with my mouse just for the challenge of it there. There we go. 1.89. That's my best shot at an M, a P, and an A. I didn't write those small so they'd fit. This is also 1.89. M, I'm not going to have room for all that. P and A, that's the best I can do, okay? So that's how you can draw up those sketches if you want them. Now we'll touch on how to do it numerically here in a little bit. Okay. Let's see here. So there's a sketch showing the shear and normal stress on the plane AB at 118 degrees. So I went ahead and calculated that. They're both positive. So there's a positive normal stress in tension that's normal to the plane. Right there. And there's also a positive shear that I'm drawing like a couple. That rotates counterclockwise around that plane. Okay, right there. All right. All right, this next one here, we know that we've got a line there. From A to B, I think it is, that can only handle 1,400 pounds per square inch. So what I'll do there is I'll figure out how much torsion can be applied to the shaft. So I calculate the moment of inertia. Pi over 2 times the outer radius, half of 9, that's 4.5 to the 4th power, minus half of 6, 3 to the 4th power, comes out to be 517. Okay, I know the normal stress is tau xy times sine 2 theta. So if I solve that for tau xy, I get sigma x1 over sine 2 theta. 1400 psi is what the most I can apply to that plane. Theta is not 75. Theta is measured from the vertical counterclockwise, so that's 15. Twice 15 is 30. So 1400 over sine 30 is 2800 psi. Okay, so what I do there, I find the shear stress based on equating that to sigma x1 over sine 2 theta. I find that by just rearranging this normal stress equation here. So I get tau xy as sigma x1 over sine 2 theta. All right, so now I take the basic shear stress equation. Tau is TR over I, and I rearrange it and solve for T. Now notice that T is the torsion. That's the letter T. Tau is the shear stress. That's the Greek letter tau. Okay, they're different. So the torsion is tau, the shear stress, times I over R. I'm just rearranging that equation to solve it for T. Plug in tau, I, and R, and I get 321,689 pound-inches. So that's the torsion that can be applied, such that we will have a stress on plane AB of 1,400 pounds. You could divide that by 12 also, and based on that come up with the foot-pounds also. Okay. So that'd be 26,807, I think, or maybe 867, I can't tell. Pound-feet, foot-pounds. Okay. Okay, the next one here is 302. Now on this one we've got a shaft, and we've got 3 constraints on it. It's a solid shaft. And we've got 3 things that have to be met. The shear stress can't exceed 1,400 psi. The normal stress can't exceed 22,000 psi. And the angle of twist can't exceed 1.75 degrees. The shaft has to develop 125 horsepower with a rotational speed of 600 RPM. How big of a shaft do we need to use? Okay. So this first page here, I'm just doing, or first slide maybe I should say, I'm just doing conversions. I've got 125 horsepower, that's the common imperial unit for power. 550 foot-pounds per second per horsepower, 12 inches to a foot. That gets me 825,000 inch-pounds per second. Okay, that's the power. .600 revolutions per minute. 1 revolution is 2 pi radians. 1 minute is 60 seconds. Run that through, I get 62.8 radians per second. That's the angular speed. Now to solve this thing out, I want to find the torsion. Power is torsion times angular speed, so torsion is power divided by angular speed. So if I divide that out, I'll get the torsion in the shaft, 13,130 inch-pounds. Also in our formulas here, we need to input angles as radians. So that angle of twist, 1.75 degrees, is pi radians over, or multiply that by pi radians over 180 degrees. I get 0.03054 radians. So that's the twist angle. All right. Now, once I've got that, I'll use this formula here. And what I want to do, I'm going to solve for the radius of the shaft. Tau max is TR over I. That's also sigma max. They're both equal to that. Now, what I is pi over 2r to the 4. And I can simplify that. I'll take the 2 up to the top of the equation. So I'll move that from the denominator up to the numerator. That's 2tr over pi r4. And then I'll cancel the r with one of these. So that'll leave me r3 on the bottom. So I'll have 2t over pi r3. Okay, and that's equal to sigma max and tau max. Okay, I'll multiply through by r3 and divide by either sigma max or tau max, and I'll get these two formulas. R3 is 2t over pi tau max, and R3 is equal to 2t over pi sigma max. Take a third root, and I'll solve for the radius. So what I did, I just took these equations and pulled the radius out and solved for it. Okay. Now I have to realize that the radius is part of the I equation. So I have to take I and turn it in to pi over 2 r4. That way I can solve for the radius. Okay. So I just plug in everything. 2, I've got t is 13,130. Pi, and then I've got tau max is 1400, sigma max is 2200. I just plug all that stuff in, take a third root, okay, which ought to be to the 1/3 power, either way, whatever you got on your calculator, you can do it. And that's 0.842 inches for tau max, and 0.724 inches for sigma max. So those are two values that I've got so far. I need to do one more for the twist. Okay. So what I'm doing, I'm just solving for these allowable values. I've got tau max at 14,000, sigma max at 22,000. And I'm running those through this formula I've developed and solving for the radius for both cases. Okay, one more thing I got to check is the angle. Phi is the angle of twist. TL over IG. So that's TL over pi over 2 R4G. Bring the 2 up. That's 2TL over pi R4G. Solve for R4. It's 2TL over pi phi, which is the angle of twist, times G. So my final formula here, I take a fourth root of 2TL over pi phi G. Plug in everything. Take a fourth root, which I think is to the 0.25 power. So just plug all these values in, and I get 0.952 inches. So I've solved for all three values for each of the three constraints: tau max given, sigma max given, phi max given. Now, when you're designing things, which is what we're doing here, you go with the biggest size. So we got three possibilities. Go with the biggest one. So that's the safest thing to do, to go with the biggest. 0.952. That's a radius. Double it, you get the required diameter, 1.9 inches. Okay. So that's 302.